My name is Robert Ramey. I am the author of Safe Numeric Library, which has been proposed as part of the C++ standard. And also, there's a different version of it with the same name, which has been proposed for inclusion into Boost. The question arises, and it's very interesting. I proposed this talk 4 times. 4 times it's been rejected. The only reason that I'm here today is I managed to tailgate behind John's so I would get a spot here. The question that always arises is, what the heck do we need this for? We already have, within the C++ language the built-ins, integers, longs, unsigned, etc. What's the point of this whole exercise? And here it is. Here, this z equals x plus y. This is a simple thing we do all the time. It's transparently obvious what it's supposed to do. And yet, in this particular example, it will not return the result we expect to return. If we add 2 integer values, these are int 8s, which are out of the C standard library, or C++ standard library, it will produce a value of 199, and then when we try and store it into an integer again, it will overflow and we'll come up with a different value. A lot of times we don't see this because the values we're using don't exceed the capacity of the integer types we're using. But it's a common problem that's occurred forever, it still occurs, and people just then they go in, and after the car crashes, then they run a debugger or whatever. That's one kind of problem that occurs. Another kind of problem is if we take an integer value and change it to an unsigned integer. Here, the same thing. We've taken a value of 129. Actually, I see that this is a mistake. It's very easy to make a mistake here. And if I change the sign of something, it will actually change the value as well. I have to update my example there. It should probably say, oh no, that's correct, what I'm saying. It's unsigned integer, I'm storing in an 8-bit integer, it's of a value of 129. If I assign that to a signed integer, it changes it to a -2. This is something extremely common, it happens all the time in small systems. In bigger systems it happens, but people don't notice it because it doesn't happen very often. And the truth is, there's no compile problem here. There's no execution problem. It just, your program blunders on with the wrong result and keeps going on. There's no way that you can tell your boss, the government, or even yourself that this thing has that you know for a fact that this has a correct answer. Here's another problem. It's extremely easy to input from an external source an integer whose size exceeds the capacity of the integer variable you're loading it to. If you run this code, again, it will compile without problem, it will build without problem, and you run it, X and Y will not contain the values that you specify here. What you see is not what you're getting. You cannot verify that your program is working by inspection, even if your program is just 1 line long. Pretty clear, right? Moving on. What's the solution? Well, people have been talking about this for 20 years, and the solution is really, the only really solution is to know what you're doing, and don't do that. That is, frankly, of no value. Here is what's recommended by the Software Institute on their C-Cert Security Coding Standard, which is the standards of rules that you should follow to generate a program in C or C++ which does not have, which is correct. Their suggestion is that you replace the X and Y with a construct like this. Now, it's ridiculous. There's just no other way to say it. There's no way that somebody's going to go through and change all their simple addition operations to include code like this. Besides the fact that it would depend on a particular integer type, et cetera, et cetera. But the fact that this is even proposed outside of a comedy club is frankly an embarrassment to our profession. And take this. I mean, I just showed the ridiculously simple idea, just addition of two numbers. What happens if you have an expression just slightly more complex? Two numbers multiplied and then added to another one. Now you're going to decompose this into several functions, and each one apply this checking to know you get the right answer? I mean, that's even more ridiculous than the first example, which was already ridiculous. So, and yet that's the state of C and C++ today. And nobody is telling me that this has a fix, or nobody's proposing anything. Except till now. So here's the real solution. The real solution is you use the Boost Safe Numeric Safe Integer Library. You just take all the places in your program where you use an int, a long, an 8-bit integer, an unsigned or whatever, and you just wrap each one in this safe template. You recompile your program and you run it, and now anytime any of those previous situations occurs, you will get an exception. It's that simple. You don't have to change anything else. Matter of fact, if you're like super picky and paranoid, you just wrap this up into a typedef or a template alias, and then you could switch back and forth on the fly. But why would you want to do that? Well, every time I propose this, so finally I get somebody to listen that the whole C++ integer system is totally broken, and they'll say, well, what's your solution? I say, this is the solution. And what do they tell me? What's it cost at runtime? How much does it slow down my program? Well, that depends. In many cases, for example, this illustration here, if I take two 8-bit numbers, I add them together, well, that's possible that might exceed more than 8 bits. C++ and C type promotion rules actually will use an intermediate type for that, which is larger, either 16 or 32 bits, or I don't know, whatever the machine supports as its natural integer size. It will do the addition. So you won't get an overflow at that point. And then when you assign, and I happen to know that two 8-bit integers added together, even if they're the maximum they can be, will easily fit within a 16-bit number. So in this case, the safe integer library injects no extra code into your program. The runtime cost is absolutely zero. So now, of course, the question is, aha, I got you. What's going to happen if it's larger sizes? Is this always true? Of course it's not true. It means the way C and C++ are today, that there will be a runtime cost with this. So you're right now stuck in a quandary. As a craftsman and a C++ programmer, it's going to be your job to install this code, run your profiler, and then fix all the places either by changing the types or decide that the runtime cost is so small that it's not a problem. If you do that, then you will be among the 1/10 of 1% of C++ programmers in the world who can tell your boss or the guy sitting behind your self-driving car that this program will not fail. Will you get an increase in salary for that? Probably not. But you won't be embarrassed. How about that?
They're not using safe integers.
Whatever. No, I think that's a whole nother issue, which is subject of my other talk. Okay, so I've got two, and so now actually that's everything all you need to know to use this library, I've already told you. I have two versions of it. Excuse me, I have a proposal for the C++ committee. You know, that's winding through the thing. I kind of almost don't care anymore because it's just a hassle. And there is, the real library is submitted to Boost. It's on the Boost library incubator. And it has a lot more capability than I've described here. It has the ability to, using policy classes, to change. Right now, what I've described, it throws an interrupt, and, it throws an exception, but you could have it do other things, call a special function. It has the concept of an error handling policy. The issue of type promotion, as John talked about, elastic integer, it has the ability to to change the types of results to make sure they're large enough to hold the result. I think that's functionally identical to the elastic integer concept that John was talking about. And in fact, you can specify the type promotion policy. It turns out there's a number of reasons why you might want to do that. You might want to run code that runs on an embedded system. I actually use this to test code that runs on an 8-bit processor, and I changed all the types to replicate the types that were used on that 8-bit processor, so I could run my test code on my machine, on my PC, and know that it will not crap out when I run it on this medical instrument, which is driving some guy's heart. So that's it. Nothing to it. Any questions?
Yeah, I got one.
Thank goodness.
So you talked about like automatic promotion. What happens when you try to multiply two unsigned 64-bit integers?
Okay, well, if you multiply, the question is, how does the type promotion work? Is that a fair rendering of your question? Yeah. And first of all, that's not such a subject to my talk, but I'm going to answer it anyway. And because this is a feature of the library, which is posted, which is available for use, and you can try out. And the way that it works, and the only way that it can work, is using template metaprogramming when two safe integers are multiplied, and you have the type promotion policy selected, so it's the one's called automatic, then it will say, aha, two unsigned integers. The only way that I can actually guarantee to hold the result of that is if I have an unsigned log. So I will promote both of the constituent operations from unsigned integers to unsigned log and then do the multiplication, and then I know that it will not exceed the capacity of an unsigned log. Right? Does that make sense? Yeah. And it's zero cost. You don't have to check for overflows or anything like that because you know the range of the initial variables, you know the range of the result, and you know that range fits in the final result. So in that case, the only runtime cost is promoting your constituent variables to a larger size so that the C++ multiplication machinery can work. Because the C++ multiplication machinery always creates a type which depends on your constituent types. So you have to promote your constituent types in order to get a result that's big enough. By the way, what this means is it has to do all the range arithmetic of compile time on all integers. It's a lot more difficult to implement than first meets the eye. And the beauty of it is I can explain in 10 minutes what it does. Take me 10 hours to explain how it does it. But you people have the huge benefit, you don't even have to care about that. In 10 minutes, you can probably find a bug that's been bugging you for years. Anthony. Okay, there's two differences. Well, there's two. One is, the question is, there's some compilers which have compile time switches which detect some of these problems. Okay, there's a couple issues with that. To start with, there are certain things like overflow of unsigned integers, which is defined behavior and not trapped. I've chosen to trap it because I think it's a mistake. Second problem is what that, in the Intel processor, that sets a particular flag. C++ doesn't have a syntax to really deal with that flag. Third, that's really an implementation issue. Now, I implemented this in a totally portable way. Now, somebody who's got nothing else to do and is concerned about that would say, want to take it the way I implemented it and specialize some of the functions that they might take advantage of that flag. Yes, sir.
Can I make the error handling to go to a type like optional or so that I can continue on calculating instead of like catching an exception all the time, just to have at the end the result where I know it's
okay. The question is, can we customize the error handling? And the answer is, on the proposal I made to the C++ Standard Committee, I didn't include that facility because I wanted to keep a standard library proposal simpler. For the one that's currently in the Boost review queue, it has the ability for any type to specify an error policy. And there's a couple of them in there, and one of them is the default one is to throw an exception. Another one is you can call your own particular function. Another one is you can just ignore it. And there's another one is to just trap at compile time. So that if you decided, I want 0 runtime overhead, I set the policy so that it just requires me to fix up the types so that this will never happen. So there's 4 different error policies already in there, and of course, you're free to put in your own if you'd like. Now, the real answer to your question would be, is you don't want to do that. What you really want to do is to trap those interrupts low enough in your program so that you could recover and redo the operation in a different way. Right? If you catch the interrupt lower, then you wouldn't have a problem. Anyway, without going into too much detail, you can pretty much do anything you want there. Yes, sir.
Yeah. I have 2 questions. What would be the result of a safe unsigned char plus a safe unsigned char? And what would be the result of unsigned char plus a safe unsigned char?
Let's take the first one. What's the result of adding 2 safe unsigned chars? Well, it's actually, if you follow the normal type promotion policies which C++ supports, what you'll get is an unsigned int. Look it up in the standard. If I add 2 unsigned chars, each one is promoted to an unsigned int. I could be wrong. The standard is pretty dense. But anyway, what happens in the C++ and C world, it's the same thing. It tries to elevate the types to a common type, which is of a certain size. The safe integer library, by default, doesn't intervene in that process. It just traps it if it's going to result in an invalid value. I think that answers the second question, too. Huh? Okay. Yes, sir. Yeah, well, you...
So I was going to ask, so presumably, if I were implementing this, my immediate instinct would be to have an operation, in addition, for example, between 2 safes, return an intermediate, like let's call it an unsafe, and then assigning that to a safe is when the check can either be short-circuited if we know 100% that it can't be an illegal cast, or do the necessary checking if it's possible. Is there anything more, I guess, clever beyond just the promotion?
You know, that's, how should I say? It's really clever. And the way you describe it is exactly right. It's actually when you do it, when it starts to require a lot of cleverness. Huh? But basically, it overloads all the integer operations. And then including the assignment, and including operations for which one type is an integer and the other type is an unsafe integer. So you know, if you think about it, you can pretty much see there's only one way to implement it, which is pretty much overloading everything. Yes, sir.
So is it possible to compose the fixed point proposal with the safe proposal?
Well, that would be not up to me, but let me make a broader answer. Anywhere you use an int, the intention of this library is to be a drop-in replacement, so that any library that you use that takes a template parameter that has integer characteristics, you should be able to substitute the safe equivalent and have everything work as before.
So that would be your proposal for how to compose it. To use the safe end.
It's my intention and it's my proposal and it's my belief that the concept of integer safety should be orthogonal to any other concept.
I have managed to specialize fixed point with safe. There are some limitations to that. There isn't currently float to safe conversion, and fixed point really likes to go back and forth between fixed point and floating point.
Okay, I'm informed the session's over. Thanks for coming. I hope you enjoyed it. And good luck, you know, you guys that are writing the programming for self-driving cars.